Welcome to Chapter 11 of Class 10 Science, Electricity. In this fascinating chapter, we'll explore one of the most important discoveries that powers our modern civilization. Electricity has revolutionized our world, from lighting our homes to running industries. But have you ever wondered what electricity really is? How does it flow through wires? What controls the amount of current in a circuit? We'll answer all these questions as we study electric current, potential difference, Ohm's law, resistance, and the heating effect of current. This chapter builds on our understanding of physics to explain the fundamental principles that make electrical devices work. Get ready for an electrifying journey through the world of circuits and currents. Let's begin with the fundamental concept of electric current. Just like water current is flowing water, electric current is the flow of electric charge through a conductor. When electric charges flow through a metallic wire, we say there is an electric current in the conductor. Think about a simple torch. The cells provide the flow of charges through the bulb to make it glow. The switch creates a conducting link between the cell and the bulb. A continuous and closed path through which electric current flows is called an electric circuit. We express electric current mathematically as the amount of charge flowing through a particular area in unit time. The formula is I equals Q divided by T, where I is current in amperes, Q is charge in coulombs, and T is time in seconds. Interestingly, in metallic wires, it's actually electrons, which are negative charges, that constitute the flow. But by convention, we take the current direction as opposite to electron flow, from positive to negative terminal. Now let's understand what makes electric charge flow in the first place. Charges don't flow by themselves in a wire, just as water doesn't flow in a horizontal pipe. There needs to be a difference in electric pressure. This is called potential difference. A battery produces this potential difference through chemical action. When connected to a circuit, this potential difference sets the charges in motion, producing electric current. We define potential difference between 2 points as the work done to move a unit charge from one point to another. The formula is V equals W divided by Q, where V is potential difference in volts, W is work done in joules, and Q is charge in coulombs. 1 volt equals 1 joule per coulomb. We measure potential difference using a voltmeter, which is always connected in parallel across the points where we want to measure the voltage difference. Unlike an ammeter that measures current and is connected in series, a voltmeter has high resistance to draw minimal current from the circuit. Before we proceed further, let's learn how to represent electrical circuits using standardized symbols. Circuit diagrams use specific symbols to represent different components, making circuits easy to understand regardless of language or location. An electric cell is represented by a long and short parallel line, with the longer line representing the positive terminal. A battery is multiple cells connected together. A switch in open position is shown as a break in the line, while a closed switch completes the circuit. An electric bulb is represented by a circle with a cross inside. A resistor is shown as a zigzag line. An ammeter is represented by a circle with a inside, connected in series. A voltmeter is shown as a circle with V inside, connected in parallel. When drawing circuit diagrams, we should use standard symbols, draw straight lines for wires, show clear connections at junctions, label components clearly, and keep the diagram neat and organized. Now let's explore one of the most important laws in electricity, Ohm's law. In 1827, German physicist Georg Simon Ohm discovered the relationship between current flowing through a metallic wire and the potential difference across its terminals. He found that for a given metallic wire at constant temperature, the potential difference across its ends is directly proportional to the current flowing through it. Mathematically, we express this as V proportional to I, or V equals I times R, where R is the resistance of the conductor. We can rearrange this formula to get I equals V divided by R, or R equals V divided by I. We can verify Ohm's law experimentally by setting up a circuit with a nichrome wire, ammeter, voltmeter, and cells. For different numbers of cells, we note the current and voltage, calculate the V by I ratio for each reading, and plot a VI graph. The graph is a straight line through the origin, confirming that V proportional to I at constant temperature. Let's now understand resistance in more detail. Resistance is the property of a conductor that resists the flow of electric charges through it. Its SI unit is ohm. When electrons move through a conductor, they are restrained by attraction from atoms. This opposition to electron flow is called resistance. Good conductors like copper have low resistance, while poor conductors have high resistance. Through experiments with nichrome wires of different dimensions, we find that resistance depends on three main factors. First, length. Resistance is directly proportional to the length of the conductor. Double the length, and resistance doubles. Second, area of cross-section. Resistance is inversely proportional to the area. Double the area, and resistance halves. Third, nature of material. Different materials have different resistivities. Combining these relationships, we get R proportional to L divided by A. Now let's discuss resistivity, which is a fundamental property of materials. Resistivity, represented by the Greek letter ρ, is the resistance of a material of unit length and unit cross-sectional area. It characterizes how strongly a material opposes electric current. The SI unit of resistivity is ohm meter. Lower resistivity means better conductor. For example, silver has the lowest resistivity at 1.60 times 10 to the power minus 8 ohm meter, followed by copper at 1.62 times 10 to the power minus 8. Aluminum has higher resistivity at 2.63 times 10 to the power minus 8. Alloys like nichrome have much higher resistivity, around 100 times 10 to the power minus 8. Semiconductors like silicon have even higher resistivity, around 2300 ohm meter, while insulators like rubber can have resistivity as high as 10 to the power 16 ohm meter. This is why alloys like nichrome are used for heating elements. They have high resistivity which produces more heat, don't oxidize easily at high temperatures, maintain mechanical strength, and their resistivity doesn't change much with temperature. Now let's explore how resistors behave when connected together in series. When resistors are connected end-to-end, so that the same current flows through each resistor, they are said to be connected in series. In series connection, there is only one path for current to flow. If any resistor fails, the entire circuit breaks and current stops. In series combination, the equivalent resistance is simply the sum of individual resistances. So Req equals R1 plus R2 plus R3 and so on. The characteristics of series connection are: the same current flows through all resistors, the total voltage equals the sum of individual voltages across each resistor, and the equivalent resistance is larger than any individual resistance. For example, if we have three resistors of 5, 10, and 15 ohms connected in series to a 12-volt battery, the equivalent resistance is 30 ohms, the current is 0.4 amperes, and the voltages across the resistors are 2, 4, and 6 volts respectively. Notice that the largest resistor gets the highest voltage drop. Now let's examine parallel combination of resistors. When resistors are connected between the same 2 points, providing separate paths for current, they are said to be connected in parallel. In parallel connection, the voltage is the same across all resistors. If one resistor fails, current continues through the other paths. In parallel combination, the reciprocal of equivalent resistance equals the sum of reciprocals of individual resistances. So 1 divided by Req equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3 and so on. The characteristics of parallel connection are the same voltage across all resistors, the total current equals the sum of individual currents through each resistor, and the equivalent resistance is smaller than the smallest individual resistance. For example, if we have 3 resistors of 5, 10, and 30 ohms connected in parallel to a 10-volt battery, the equivalent resistance is 3 ohms, the total current is 3.33 amperes, and the currents through individual resistors are 2, 1, and 0.33 amperes respectively. Notice that the smallest resistor carries the largest current. Now let's explore the heating effect of electric current, which is described by Joule's law. When electric current flows through a conductor, the conductor becomes hot. This is called the heating effect of current. The heat is produced due to the resistance offered by the conductor to the flowing current. As electrons move through the conductor, they collide with atoms, transferring kinetic energy which appears as heat. Joule's law states that the heat produced in a resistor is directly proportional to the square of the current, directly proportional to the resistance, and directly proportional to the time for which current flows. Mathematically, H equals I squared times R times T, where H is heat in joules, I is current in amperes, R is resistance in ohms, and T is time in seconds. This heating effect has both useful applications like electric heaters, toasters, and bulbs, as well as problematic aspects like energy loss in transmission wires and overheating of devices. Let's look at some practical applications of the heating effect of electric current. In an electric bulb, the filament, usually made of tungsten, gets heated to a very high temperature of about 2500 degrees Celsius and starts glowing, emitting light. Tungsten is used because it has a high melting point of 3422 degrees Celsius, can be drawn into thin wires, and doesn't oxidize easily when the bulb is filled with inert gas. Interestingly, only about 5% of the electrical energy converts to light, while the rest becomes heat. Another important application is the electric fuse, which is a safety device that protects electrical circuits from excessive current. A fuse is made of material with low melting point like tin-lead alloy, connected in series with the circuit. When current exceeds the rated value, the fuse wire melts, breaking the circuit and protecting appliances. Heating devices like electric heaters, irons, and kettles all use high-resistance wires that produce heat when current flows through them. Now let's understand electric power, which is the rate at which electric energy is consumed or dissipated in an electric circuit. Power tells us how fast electrical energy is being converted into other forms like heat, light, or motion. The SI unit of power is watt, where 1 watt equals 1 joule per second. We can calculate power using several formulas. P equals V times I, or using Ohm's law we get P equals I squared times R, or P equals V squared divided by R. For example, a 60-watt bulb converts 60 joules of electrical energy to light and heat every second. An interesting phenomenon occurs when bulbs of different wattages are connected in series. The bulb with higher resistance actually glows brighter in series connection because the same current flows through both, and power equals I squared times R. So the bulb with higher resistance consumes more power and glows brighter, which is counterintuitive but mathematically correct. Finally, let's discuss the commercial unit of electrical energy, which is the kilowatt-hour, commonly called a unit. 1 kilowatt-hour is the energy consumed by a 1 kilowatt device in 1 hour. Since 1 kilowatt equals 1000 watts and 1 hour equals 3600 seconds, 1 kilowatt-hour equals 1000 times 3600 equals 3,600,000 joules, or 3.6 times 10 to the power 6 joules. Electricity bills show consumption in kilowatt-hours. To calculate energy consumption, we use the formula, energy in kWh equals power in kW times time in hours. For example, a 100-watt bulb used for 10 hours consumes 100 times 10 divided by 1000 equals 1 unit. Understanding your electricity bill helps in energy conservation. A typical bill shows current reading, previous reading, units consumed, rate per unit, fixed charges, taxes, and total amount payable. Being aware of energy consumption patterns can help reduce electricity bills and conserve energy. Let's summarize this comprehensive chapter on electricity. We learned that electric current is the flow of electric charge, expressed as I equals Q divided by T, with unit ampere. Potential difference is the work done per unit charge, V equals W divided by Q, with unit volt. Ohm's law states that V equals I times R at constant temperature. Resistance depends on length, area, and material of the conductor, with resistivity being a characteristic property. In series combination, equivalent resistance is the sum of individual resistances, while in parallel combination, the reciprocal of equivalent resistance equals the sum of reciprocals of individual resistances. Joule's law gives us the heating effect formula H equals I squared times R times T. Electric power P equals V times I equals I squared times R equals V squared divided by R, with unit watt. The commercial unit of electrical energy is kilowatt-hour. This chapter provides the fundamental understanding of how electricity works, which is essential for understanding more advanced concepts in physics and for practical applications in daily life.